Welcome back to Physics 191. I'm Gerard Blanchard. Last time we revisited equilibrium situations. When we first introduced equilibrium situations, we dealt with them using Newton's first law. The total force vector on an object is equal to zero. That means that when an object is at rest and remains at rest, or is moving at constant speed in a straight line, then the total force on that object in the x direction is equal to zero, and the total force on that object in the y direction is equal to zero. In revisiting equilibrium, we've added the condition that the total torque on an object is equal to zero, because when an object is not moving and stays not moving, we take that to mean that it's also not rotating and stays not rotating. This is the situation that engineers would call statics. So an object that's not moving and stays not moving, and is also not rotating and stays not rotating, is subject to three conditions. The total force in the x direction is equal to zero, the total force in the y direction is equal to zero, and the total torque on the object is equal to zero. And remember that torque depends on three things. It depends on the force that is applied to an object. It depends on where the force is applied to the object, or in other words, the distance from the pivot point that the force is applied to the object. And it also depends on the sign of the angle between the direction of the force and the direction from where the force is applied to the pivot point. So those are our three conditions, or our three equations that we apply when we model equilibrium situations now. Let's take a look at another example of applying those equations to a situation. A mountain climber is rappelling down a vertical wall. The rope attaches to a buckle strapped to the climber's waist 15 centimeters to the right of his center of gravity. If the climber weighs 770 newtons, find the tension in the rope and the magnitude and direction of the contact force exerted by the wall on the climber's feet. Now in the diagram we can also see that the rope is making an angle of 25 degrees with respect to the vertical. We can also see that the climber's center of gravity is 91 centimeters from the wall, and the rope is attached to the climber 106 centimeters from the wall. So the object at the center of our consideration is the climber, and the forces that you should consider on the climber are the vertical force exerted by the wall on his feet, the horizontal force exerted by the wall on his feet, gravity, or the climber's weight, which we will treat as if it were a single force exerted on his center of gravity, and the tension in the rope. So at this point, I would like you to diagram the situation, list your knowns and unknowns, think about the type of situation we have here, which is a static or equilibrium situation, and write down the equations that apply to the situation, and then work on solving those equations. Okay. Our object of consideration is our person, which I will just model as a rod. The forces on the person are the vertical force, call it F V, the vertical force that the wall exerts on his feet, the horizontal force, FH, that the horizontal force that the wall exerts on his feet, gravity, weight, which we're told is 770 newtons, and the tension in the rope, which is, we're told that the vertical angle, the angle right here, the angle that the rope makes with the vertical, so the angle here is 25 degrees. So the angle that I'm more interested in is the angle right here, which would be 90 minus 25, or 65 degrees. Okay, and we also have to note how far these forces are from the wall. His weight, or his center of gravity, is 0.91 meters away from the wall, and the rope is attached 1.06 meters away from the wall. Now, we have all of the information that we were given, and so we will identify this as an equilibrium situation, and we can write down our equations. Force total X is equal to 0. Force total Y is equal to 0. And torque total is equal to 0. In order to calculate torque, we will have to identify a pivot point. Even though he's not rotating, since he's not rotating, we can take any point to be the pivot point around which he's not rotating. And it's most useful to pick a pivot point where you have the most unknown forces. You'll see why in a moment. So I am going to recommend that we pick his feet to be the pivot point. His feet are the pivot point. Okay, forces in the x direction. Well, we have to draw our axes, our x-axis and our y-axis. Our forces in the positive x direction, we only have one, and that is the horizontal force. So FH is in the positive x direction. In the negative x direction, we have a component of the tension of the rope. We'll have to break the rope up, the tension of the rope up, into adjacent and opposite sides. So this side right here would be tension adjacent to our 65-degree angle, and this side over here would be tension opposite to our 65-degree angle. And the side that is in the negative x direction is the adjacent component of tension. So we would have FH minus tension adjacent equals 0. That tells us that the horizontal force is equal to the adjacent component of the tension. That tells us that the horizontal force is equal to the tension in the rope times the cosine of 65 degrees. And that's all that we can do this far, because we don't know the horizontal force and we don't know the tension, so we'll have to pause with our x equation and move on to our y equation. Let's see what we get there. Well, our forces in the positive y direction are Fv plus part of our tension, namely the part that's opposite to the 65-degree angle, so plus tension opposite, and then minus our weight. Weight is in the negative y direction, so minus 770 newtons equals 0. That tells us that force vertical is equal to 770 newtons minus tension opposite. I've added 770 newtons to both sides, and I've subtracted tension opposite from both sides. That tells us that the vertical force is 770 newtons minus tension cosine of, sine, that should be sine because we're dealing with the opposite side, tension sine of 65 degrees. We're dealing with tension opposite the angle is sine. So tension sine of 65 degrees. And once again, we're faced with a situation where we have two unknowns in the same equation. Taking our two equations together, we have three unknowns in two equations. We have force horizontal, tension, force vertical, and tension again. So we have three unknowns in two equations. We'll have to pause again and move on to our third equation and see what breaks loose with that. Okay, our torque equation. Remember that torque is a force that's applied at some distance from a pivot. So when we look at, since I've put my pivot point right here, both the vertical force and the horizontal force exert no torque because they're applied at zero distance from the pivot. That's why I choose to put the pivot there where I have the most unknown forces to eliminate those unknowns from this torque equation. That leaves me with two forces, tension, which is pulling the person around in this direction or in the counterclockwise direction, which remember is a positive torque. Weight is pulling the person around this way around the pivot. Weight is pulling him down. And if we were to follow that around, we would go clockwise around the pivot or in the negative direction. So our positive torque comes from the tension. So our positive torque is tension times the distance that the tension is from the pivot times 1.06 times the sine of the angle that the tension makes with the person, which is 65 degrees. And then I have to subtract off my negative torque, which comes from weight. And so the negative torque is the weight of 770 newtons times the distance that the weight is from our pivot point times 0.91 times the sine of the angle that weight makes with the person, which is 90 degrees. And all of that is equal to 0. So now we can see here that we have an equation with only one unknown in it, only tension. So by putting our pivot point here, we've eliminated these two unknowns from our torque equation. So our torque equation only has one unknown, and now we can solve for it. And that would be tension is equal to 770 newtons times 0.91 meters times sine of 90 degrees divided by, and these should have meters in here since I've uncharacteristically written my newtons in, I have to write in meters as well. Keep all of my units in. Divided by 1.06 meters times the sine of 65 degrees. And we can calculate our tension. 770 times 0.91 times the sine of 90. I don't really have to do sine of 90 because we know that the sine of 90 is 1. So we're just multiplying by 1, divided by 1.06 times the sine of 65 degrees. And that gives us a tension of 729 newtons. So now we figured out our tension. 770 times 0.91 times the sine of 90 divided by 1.06 times the sine of 65 gives us 729 newtons. Now we know everything we need because we can take this tension of 725 newtons, put it in here, and also put it in this equation, and we can calculate the vertical force and the horizontal force. So force vertical is equal to 770 newtons minus 729 newtons times the sine of 65 degrees. And so the vertical force is 770 minus 729 times sine of 65, which is 109 newtons. And finally, the horizontal force exerted on the climber's feet is 729 newtons times the cosine of 65 degrees, or the horizontal force is 729 newtons times the cosine of 65, which would be 308 newtons. And so there we have our answers. We'll just review what we did here. We drew our climber. We drew in the forces that were on our climber, the horizontal force, the vertical force, the weight, which we applied at his center of gravity, and the tension, which we broke up into X and Y components. We knew the location where the forces were applied, and we identified this as an equilibrium situation, which meant that we could write total force in the X direction as 0, total force in the Y direction as 0, torque total 0, which gave us these equations right here, which means that we modeled the situation, and then we just solved our model to get our answers. The tension in the rope is 729 newtons. The vertical force on his feet is 109 newtons, and the horizontal force straight out from the wall is 308 newtons. Let's take a look at another example. A sign is supported by a uniform horizontal boom of length 3 meters and weight 880 newtons. A cable inclined at an angle of 35 degrees with the boom is attached at a distance of 2.38 meters from the hinge at the wall. The weight of the sign is 120 newtons. What is the tension in the cable, and what are the horizontal and vertical forces, Fx and Fy, exerted on the boom by the hinge? You can see the situation in the diagram. You're given the angles and the distances. This is very similar to the example that we just worked with the climber. We've only added an additional force, which is the weight of the sign hanging from the end. That's just going to apply another force onto the boom. The boom is going to be our central object in this situation. So please model the situation, meaning draw your diagram, list your knowns and unknowns, and write down your equations, and start solving for the questions that you were asked. Once again, we draw our boom, which is just a rod, very similar to our abstract person that we drew in the last exercise. The forces are very similar. We have the horizontal force and the vertical force at the wall at one end. We have weight of the boom itself, which is 80 newtons. We have the tension, which is pulling up at an angle of 35 degrees to the boom, and we know that we're going to break that up into tension opposite and tension adjacent. We have the sine pulling with the weight of 120 newtons on the end on the end of the boom, and we're given the distances of all of these forces. 1.5 meters for the weight of the boom itself, 2.38 meters for the cable, and then the weight at the end is 3 meters from these are all meters, and these are newtons, 3 meters away from the end of the boom, from the wall. Once again, I'm going to recommend that we put our pivot point at the wall where we have the horizontal and vertical unknown forces. At this point, we have drawn our diagram, listed our knowns and unknowns, so we will bring out our equations. Force total X is equal to 0, force total Y is equal to 0, and torque total is equal to 0. And let's see what each of these gives us. In the X direction, we have force horizontal, we have our X-axis and our Y-axis. In the X direction, we have force horizontal minus tension adjacent equals 0. That's our only two X forces. Force horizontal in the positive X direction and tension adjacent in the negative X direction. So force horizontal equals tension adjacent, or force horizontal is equal to tension times the cosine of 35 degrees. And that's all that we can do right now with that. Let's look at our Y forces. Our Y forces are FV in the positive Y direction, tension opposite in the positive Y direction, and then 80 newtons in the negative Y direction, so minus 80, and 120 newtons in the negative Y direction, minus 120. All of that must equal 0. So that tells us that force vertical is equal to 200 minus tension opposite, or force vertical is equal to 200 minus tension times tension opposite would be tension sine of 35 degrees. Same situation as before. We have two unknowns in one equation. We'll have to go to our torque equation. Our torque equation, as you can see, is very useful for helping us deal with that third unknown, and that's why we've revisited equilibrium to put that equation in there. Okay, now we have to think about this. Force horizontal, force vertical are applied at the pivot, so there's no torque from them. The tension will pull the boom around like this. If we go in the direction of tension, we're going counterclockwise around the pivot, which is positive torque. our weight right here, 80 newtons, would carry us, would make the boom swing in the clockwise or negative direction, and similarly for our 120 newtons, that would make the boom swing in the clockwise or negative direction. So tension is our positive torque, 80 newtons and 120 newtons are negative torques. And remember, torque is equal to force times distance times the sine of the angle between the force and the line leading directly to the pivot. So that would be tension times 2.38 meters times sine of 35 degrees minus 80 newtons times 1.5 meters times the sine of the angle between 80 newtons and the distance in the line leading directly to the pivot, which would be 90 degrees, and sine of 90 degrees is 1. So I'm not going to write in sine of 90 degrees. We just know that that's 1. And we're going to have the same thing over here where we have 120 newtons at 3 meters from the pivot. So minus 120 times 3 times the sine of 90 degrees, which I'm not going to write. That's 1. And all of that must equal 0. And we have an equation with just our one unknown tension in it. So that tells us that tension is equal to, well, I'll add both of these to both sides, and I'll get 3 times 120 plus 1.5 times 80 divided by 2.38 times the sine of 35 degrees. Which gives us a tension of, let's see, we have 3 times 120 plus 1.5 times 80 divided by 2.38 times sine of 35 degrees. And that gives us 352 newtons of tension. So the tension in the cable is 352 newtons. Now, all we have to do is take that 352, put it in here to solve for FV, and put it into here to solve for FH. So FV is 200 minus 352 sine of 35 degrees, which tells us that the vertical force, 352 times sine of 35, is equal to 202 newtons. So we have a vertical force of 202 newtons and a horizontal force of, oops, I'm sorry. I made a mistake there. I did not subtract off my 200. So I apologize. That is not correct. The vertical force is 200 minus 352 times sine of 35 degrees. There we go. FV is negative 1.90 newtons. So for our vertical force, we get a negative force of 1.9 newtons. And what that means is that when we assumed that the vertical force would be upwards, we were wrong. In fact, the wall is exerting a force downwards on the boom. Or if the vertical force were not there, let's say that the boom is hinged at the wall, that there's a pin that's allowing the wall to exert a vertical force on the wall, then that hinge is pulling downwards on the boom. And if the hinge were to break, for example, then this end of the boom would go upwards, not downwards. So it takes a downwards force from the wall to keep the boom in equilibrium. And it's a very small force. It's a force of only 1.9 newtons, so a very, very small force up or down. Now for the horizontal force, we have 352, 352 times the cosine of 35 degrees. And that is 288. 288 newtons. Now, I'd just like to make a comment here about my mistake. I made a mistake, and if I had put this, if this were a homework exercise and I had put it in, I would have gotten an error, and I would have had to go back and find my error, find where I made a mistake. And what I would have done is I would have said, oh, look, here I have 200 minus something, and that can't give me 202. So 200 minus something can't give me a number bigger than 200. So I would have been able to go back over my work because I've worked things out very carefully and linearly, and been able to find my mistake and correct it as I did. So that's why I always encourage you to to show your steps, to work linearly down the page so that you can always go back and see what you did and find where you made a mistake, just like I just did. So being neat in your math is an important trait to have when you're in a physics class. Being able to reproduce what you've done means taking careful notes and neat notes. And in this case, I was able to look at what I did and spot my mistake. So just an object lesson for you. Let's take a look at another example. Find the tension in the Achilles tendon and the force that the tibia exerts on the ankle joint when a person who weighs 750 newtons supports himself on the ball of 1 foot. The normal force, N is equal to 750 newtons, pushes up on the ball of the foot on one side of the ankle joint, while the Achilles tendon pulls up on the foot on the other side of the joint. You can see this situation described in the diagram together with the distances. The distance of the ball of the foot from the tibia, where there's a downward force on the foot, is 1.28 centimeters, and the distance of the Achilles tendon from the tibia is 4.6 centimeters. So, please diagram the situation, draw in your forces, list your knowns and unknowns, and solve this, please. Okay, so we'll draw the person's foot, same as we did for the boom and for the hiker, the mountain climber, sorry. we will draw just a simple rod, and we have the tibia in the middle of the foot, not in the exact middle, but somewhere in the middle, exerting a force downwards. Call it FT for tibia. And then 4.6 centimeters to the left, so 0.046 meters to the left, we have the Achilles tendon pulling upwards. We'll call that FA. And we'll assume that these are vertically upwards and vertically downwards. And then we have the normal force to the right. And we're told that that is 750 newtons. 750 newtons. And we're also told that it is 12.8 centimeters to the right. So 0.128 meters. So we have, and we're going to treat the foot as being roughly horizontal. So we have our X and our Y axes. And so we've diagrammed the situation, drawn in our forces, listed our knowns and unknowns. We have to draw in our equations. Force total X is equal to 0. Force total Y is equal to 0. And torque total is equal to 0. Same equations as always. Now we have the total force in the X direction. Well, we don't have any forces in the X direction. So that's 0 equals 0, which is true. Not useful in this case, but it's true, still true. Force total Y is equal to 0. Well, our positive Y forces are force Achilles plus 750 newtons minus the force of the tibia, Ft, equals 0. And that tells us that force of the Achilles plus 750 equals the force of the tibia. So if we can find the force of the Achilles tendon on the foot, we can find the force of the tibia on the foot. But we still have two unknowns in one equation, so we have to go to our torque equation. For our torque equation, we have to pick a pivot point. Since I have the distances measured from the tibia, and since the tibia is an unknown force, I'm going to put the pivot point right there at the tibia. And that tells us, well, first we have to look and see whether our forces are positive or negative. The Achilles, the force of the Achilles tendon, will tend to make the foot pivot clockwise. If just the Achilles were pulling, then the foot would go clockwise around this pivot point. So that would be a clockwise or negative torque. The force of the tibia is right at the pivot, so neither clockwise nor counterclockwise, it's 0 torque. The normal force will cause the foot to pivot counterclockwise or positive around the pivot point. So this normal force gives us our positive torque. So we have 750 times 0.128, and the normal force is at right angles to the foot as we've drawn it. So that would be times sine of 90, which is 1. So we're done. I don't have to write times 1. And then we have our negative torque, which would be minus force Achilles times its distance, 0.046, times, once again, the sine of 90 degrees, which is 1, so I'm not going to write that, equals 0, which gives us an equation with one unknown in it, force Achilles, and that tells us that 750 times 0.128 is equal to force Achilles times 0.046, or 750 times 0.128 divided by 0.046 is equal to the force of the Achilles tendon. And what does that give us? 750 times 0.128 divided by 0.046 equals 2,090, where I've rounded off to 3 significant figures. 2,090 newtons is equal to the force of the Achilles tendon. And with that, we put that in there, and we have 2,090 plus 750 equals the force of the tibia. 2,090 plus 750 gives us 2,840. 2,840 newtons is equal to the force of the tibia. So you can see that even though the foot only has to support 750 newtons of weight, the Achilles tendon and the tibia each exert very large forces to counterbalance the torque of the 750 newtons, since the Achilles tendon is very close to the tibia and the toes are farther from the tibia. So there's very large forces here and here. And that answers our question. That is equilibrium revisited, where we've added into the concept of translational equilibrium, or in other words, X and Y equilibrium, we've added in the concept of rotational equilibrium, which gave us the condition that the total torque on an object is equal to 0. Well, what if we don't have rotational equilibrium? What if an object has a rotational acceleration that's not 0, meaning that the object's rotation is speeding up or slowing down? Then we have to consider our rotational equivalent to Newton's second law. When we have rotational non-equilibrium, which means that an object doesn't meet the conditions for rotational equilibrium. Remember that rotational equilibrium is that an object is not rotating and stays not rotating, or it rotates at constant angular velocity. When an object does not meet those conditions, meaning that its angular acceleration is positive or negative, its angular rotation is either speeding up or slowing down, then we have our general equation, which is our rotational version of Newton's second law, which tells us that the angular acceleration is equal to the total torque on the object divided by something that we call rotational inertia, a capital I. So angular acceleration is total torque divided by rotational inertia, or alpha is equal to tau total divided by I. Now, what is that rotational inertia? We have to calculate rotational inertia. For a single point object, for a single mass, the rotational inertia of that mass is equal to the object's mass times the distance that it is from the axis of rotation. So I, for rotational inertia, equals m times r squared, where m is equal to the mass of the object, and r is the distance that that object is from the axis of rotation. We can see from this equation that the units of rotational inertia must be units of mass times distance squared. So the units of rotational inertia are kilograms times meters squared. When we have several point objects, then we would just add together the rotational inertia of all those point objects. Now that's actually something that we seldom do because we don't in Physics 191 because we're not usually dealing with point objects that are rotating around an axis. We're dealing with extended objects like a wheel or a hoop or a sphere that is rotating and things like that. And so for extended objects, next time I'm going to introduce you to a table that will give you the rotational inertia of all of these extended objects. But what you'll notice is that rotational inertia is always going to be the product of a mass times a length squared. So that's going to stay the same. The rotational inertia is always going to be the mass of the object times some length dimension squared, and maybe it will have a multiplicative factor such as a half or 2/3 or something like that. And that's what we'll deal with most often. Now, this equation of rotational inertia equals mr squared, that you'll have to consider if, for example, you add a small mass to an extended object. That's a situation that you might be expected to deal with in Physics 191. But when we come back next time, we'll take a look at that table of rotational inertia of extended objects, and we will deal more with this topic. But for now, the one thing that you should realize is that rotational inertia is going to be the product of a mass times a distance squared. We'll come back to that next time. Until then, think physics.